Hello everyone, welcome back to our CAPE Physics paper review. In fact, we're going to continue with this paper, which is a Unit 1 paper, which is a paper 2 from the year 2016. For this paper, we have already gone through question 1 and question 2. So now we're going to look at question number 3. Question number 3 reads that after a lesson on Hooke's law, a student is asked to measure the mass of a rock sample using a steel spring, standard masses, and a meter rule. The student measured the unstretched length of the spring and then set up the arrangement as shown in figure 5. So we're going to go through this. Just to make a note of the setup right here. And I'm going to go down to the diagram so you see exactly how it was set up. And so here we have a spring, which is a steel spring, standard mass, and a stand to hold the spring. Now let's go into the first part of the question. And the first part of the question asks us to state Hooke's law. And so Hooke's law states that the extension on a spring, we can say the extension on a spring or elastic material is directly proportional. This is very important to say, directly proportional to the applied force. And this is providing that the elastic limit is not reached. Okay? All right, so once the elastic limit is not reached, then we know that the applied force and the extension are directly proportional. So that is very important to note. And you can say not reached, or we can also use the word exceeded, which is also another way to actually say it. Okay, so let's put that piece in. All right, so very important. All right, so that's Hooke's law. That's a 2-mark question. So let's go into the next part of the question. The next part of the question now states that describe how this arrangement could be used to determine the spring constant and hence the mass of the rock sample. All right, so there are a number of things we need to do. As a matter of fact, let me just quickly outline the number of marks given here. And this is a 6-mark question. So the first thing you want to do here, even though it's stated, so you may not get a mark for this statement here, but it's very important for you to note it. So let's say it's not given because it was stated in the question, as a matter of fact, which is part 1. And so the first thing I want to do, I'm going to do this by step. So the first step is to actually note the length. So you're going to note the length of the unstretched spring. So it's very important for you to note that first. Okay, so you're going to note the length of the unstretched spring. Okay, all right, the next thing you want to do is to make sure that you now add a known mass onto the spring because you want to know what the extension is. So you're going to make sure you do that next. So the second point is to add a known mass on the spring. Very important for us to note that. So once you add a known mass on the spring, what you're also going to do is to determine also the new length. So you're going to do this now after add a known mass onto the spring. All right, you're going to also determine. So determine the new length or extension of the spring. So why this is important is because once you have that known mass and that new length or the new extension, then you actually will know what mass causing what extension. So you have to make sure you note that. So remember, you would have already known the unstretched length, okay? And so the unstretched length with the new length, once you do the difference between those two lengths, then you know that will be the actual extension, okay? All right, so for example, let's say the original length of the spring is 2 centimeters, and when you add the known mass onto it, it goes to 3 centimeters. Then you know that the extension will be that 3 minus 2, okay? And that gives you 1 centimeter in extension, just to make a note of that. All right, the third thing you want to do here, let's say number 3. So the third thing you want to do here is to now add more masses. You're going to put more masses to this because it will be very important. So you're going to add more masses. And it says standard masses given in the statement. So we're going to add more masses. Okay, and these are standard masses. So let's say each mass was, say, a 10 gram. You're going to keep on adding 10 by 10 by 10, for example, right? So add more masses. And I want to make a note here as well. You will need to add at least a couple of masses. I would say roughly 6 masses will be great, or 6 points, because you don't want a graph to be too short with only 2 points or 3 points. That's not necessarily appropriate. So you're going to add as much mass as possible. Okay? So you're going to add more masses, and I'm going to make a note right here. You're going to add at least I'll say 6, okay? 5 or 6 will be good. At least 6, all right, of this standard masses. If the question will actually state the amount of mass that is given to you, then you could use those, okay? All right, so at least 6. And what you want to do next after the masses, you want to make sure that you record the extension for each mass. All right, and you want to record the extension for each mass. All right, that's very important. Now, after you do that, the next step you want to do after you have that recording, so you have a table or a chart, and after you have done that, you want to do something next. You want to plot a graph. So you're going to plot a graph. So this is number 4. The fourth thing you're going to do is to plot a graph. And the reason why to plot a graph, you want to see the relationship between the masses and the extension. So what you can do, you can have a graph to say extension weight versus extension, or mass versus extension. But it's best to use weight, because weight will be a force. Because remember, now you're looking at Hooke's law, and Hooke's law talks about applied force, so you can convert the masses into weight, okay, which is the force. You plot a graph showing the weight of the masses against extension. That's going to be very important for you to have that graph. Now, after you have done that, in terms of plotting a graph, what you want to remember now, right, is that you can consider the formula that force is equal to constant times the extension. Okay, so you can also note that formula here. But let's go into it a little bit more. Okay, we'll go into a little bit more, and just to make mention right here that what you can do, and you could actually do this in the first part where, say, you had a known mass, so we can actually get the relationship at this point from the known mass. But I'm going to tell you something here though. The reason why it's not appropriate to use the known mass and a single extension to find the constant is only one added mass. So it's not appropriate for you to actually say, okay, this is a spring constant. Using a lot of masses, right, and a number of extension and find the gradient of the graph, for example, it is best, okay? Because at least you'd include a number of masses or a number of points within your calculation, so you can know, so okay, this is more appropriate, okay? A one-time experimental result is not always appropriate for you to conclude something. So that's why the graph is best to use, and then you get your gradient. So what you can also do right here is to find the gradient of the graph, okay? So I'm going to show you something here first though. Just remember that force is equal to the constant multiplied by extension, right? So what they want to find here is the constant, which is k. So based on the graph, you're going to say from the graph, determine the gradient. So once you determine the gradient, what you're actually determining right here is the constant, because the weight, which will be on the y-axis, divided by the extension, will give you the constant. However, though, if the graph was plot in terms of extension on the y and force on the x, then it will be the inverse of the gradient to give you your constant. So also be aware of what is on the x-axis and what is on the y-axis. Okay, so from the graph, determining the gradient, right, of the graph. Determine the gradient. Okay, let's say determine the gradient and use the gradient, because the gradient will be the constant, and use the gradient to represent the constant. Okay, that's very important there. So that's how we determine a constant. Now it also tells you to find the weight of the mass, right, or the weight of the rock actually. So the next thing you want to do here now, you want to actually add the rock, or add the rock to the spring. So you're going to add the rock to the spring. All right, and the reason we're going to add the rock to the spring is actually to determine the extension by the rock. So now add the rock to the spring and record the extension, okay, and record the extension on the spring. And this extension is because of the rock, okay, and determine the extension of the spring. All right, so once you have done that and you determine the extension of the spring, what you can do now is use the extension in the formula to find the weight, okay? So once the weight is determined, so after that, now you're going to determine the weight. So after it is recorded, you add the rock to the spring, you determine the extension, and they say determine, you say determine, I could use that as the next point, determine the weight, all right, of the rock based on the extension, all right? All right, so great. And now once you find the weight, what you can do now is determine your mass, because mass now, so mass would equal to weight divided by gravity. So you can determine the mass by dividing the weight by gravity. All right, and that will be how you determine both the constant of the spring and also the mass of the rock. All right, so let's go to the next part of the question. And the next part of the question here, which is part B, is a spring manufacturer tests the properties of a spring by measuring the load applied each time the extension is increased. The graph of load versus extension is shown in figure 6. All right, and so just to point this out before you actually start answering this, the graph like this could be used in your experiment, which is the load or the weight, and versus extension, right? Which I was mentioning before. Now, I'm going to point out a few things with this graph before I actually go into answering it. All right, so I'm going to zoom into the graph to point out a few things first. All right, so let's go into the zoom of the graph. And so what I want to point out here, all right, to make it clear, is that let's say from 30 to 40, there's a point right here, right? So this would be 35. And so each of these lines will be 1, okay? So each of these lines will be a value of 1 Newton, right? And if we should go down into the x-axis, I just want to point this out again, you'll realize that for every 2 centimeters, you have a 0.01, okay? So halfway here would be 0.05, okay? So a single block will be 0.05, okay? And so each line now will be 0.005, okay? Just to make that known as well. Now, so I want to go into the question now real quick and start answering the question. So what I wanted to look at, a matter of fact, is the shape of the graph. And you notice there's point A, point B. And so something interesting is happening there. And we're going to talk about that. So here now it said use the graph to find the work done in extending the spring up to point B. You want to find the work done by extending the spring all the way up to point B. So let's look at what point B is now. So point B is all the way to the end. So what I want to look at, how are we going to find work? Because now you have a spring. I want to find work. But you must know that work is equal to, I'm putting it on the side right here. Work, right, is equal to force times distance. Do we have a force? Yes, which is the load. Do we have a distance? Yes, the extension. So the distance is the extension. The force is the load or the weight, okay? So we definitely could find work. And work is measured in joules, okay? Or Newton meters. Now, to find work here, based on the graph, what can we do? Because it's a multiplication, force times distance. So based on the graph, how can we say now the load, which is the force, multiplied by the distance, which is the extension? The only thing we can do here, let me go in a little bit more into this graph so it'll be a little bit easier for us to see. All right, so what I'm going to do, to multiply load by the extension, which is the distance, because this is in meters and this is in newtons, I will have to find the area below the graph, which is, say, base times height or half base times height, thereabout, right? So I must find the area below the graph. So let me quickly show you what will happen here now. So I'm going to draw a line here. So this line goes all the way down. I'm trying to be as straight as possible to keep it on that line. So I'm going all the way down right there. And what I get in this part is a triangle. So I could say this area is going to be half base times height. Okay. So half the base times the height. That's a triangle. And then on this side, right? Now we're going to have a little bit of problem here. So what I'm going to do now, because this is a curved line, but what I can do, I can break this up into 2 different parts. And here I'm going to go straight over. Okay, so help me out here. And I'm going straight over. Okay, great. I'm getting this as straight as possible. Great. And this piece will go all the way down here. All right, I'm trying to keep on the line. And that is a rectangle, which is going to be base times height. Now, my only problem is in this section right here. What do I do in that part? What I must do is determine what's going to happen in this section here, which I'm going to do that right now and show you what I will get. Or matter of fact, I can't even calculate it. What I'm going to do is actually to estimate it based on this on the squares or the blocks. But for me to do that, I have to know what each block or square is. So let me zoom back into the graph a little bit and show you exactly what I'm talking about. So again, remember, just to make it clear, all right, I'm going to zoom into it and show you exactly what I'm talking about. One square, right? One of these square here. Let me draw it. So one of these square, I want to make it clear to you what we're talking about, right? So from here, this will be 35 right here, right? So the height of a square right here is actually 5 newtons, right? So it's 5. Okay. So we know the height will be 5, but what will be the base? Let's go down to the bottom of the graph to determine that. All right. So I want to make sure that we know what the base is. And so remember now, coming from the 0 point to 0.01, half of this will be 0.05. Okay. So half of it will be 0.05. So let me just make a note right here so you're going to see what I'm talking about. So this here will be 0.005. All right, that's kind of big, but I actually wanted to see it, okay? So that's what that line is actually equal to. So we know now that the base of the square is 0.05 and the height of it is actually 5, okay? So this is going to be very important for me to estimate my boxes at the regularly shaped part of the graph. All right, so let's go to half base times height right here, right? The base is from 0 all the way to 2.9 because this is 2.9 because this is 0.03. So that is actually 0.0, I should say 29, okay? So my base here, just to make a note of it real quick, the base here will be 0.029. So that will be the base, okay? 0.029. That's the base from the 0 point to this point. The height, it goes all the way up to this line, which is the third line after the 30. So there's going to be 35. So we're going to multiply by 35 and then we'll divide by 2 because it's half the base times the height. So we're going to just multiply the base by the height, then divide by 2. In this region right here, the height is the same. So the height is 33. I said this is not 35, it's 33. All right, this is 33, not 35. And so the base here, starting from 0.029 and ending at 0.045, the difference between those two numbers will be 0.016. So the base here is 0.016. And we're going to multiply that by the height, which is 33 as well. Okay, all the way up to 33. Now I'm going to zoom into the graph now to show you the next part here. All right, and show you how I'm going to estimate my values. And so remember, for this graph, let me zoom into it first. So I'm going to write it on it. So it's going to be easier for you to see. All right, so I don't want to miss anything here. All right, so what I want to point out is that, again, as I mentioned, one block, the height of it is 5, and the base of it is 0.005. Okay, based on the scaling of the graph and the points that we have. Now, what I want to do, right, is to see how best I could estimate how many squares I have here. I could actually count the small ones, but I want to count the big ones. All right. So I'm going to put a different color and highlight what I'm talking about. So here, for example, if you look at this, it's only from this small section right here, and all of this section equals to about 1 square. So all of this is 1 square. Okay, 1 square. Going to this part now, I want to notice these two pieces right here, right? These two parts here that I'm going to circle equal to about half. Okay, so together they equal to about half of a square. this small little piece in the corner right here and this other region right here so it could fit right here. So if I think I'm going to do it like that, right? So this is the area and this is the area. They're almost the same. So this is almost another half again. So we have 2 halves and a 1. So we have 2 squares. Okay, we have 2 squares. And so if we have 2 squares, and remember that 1 square is equivalent to, let me go back to it, is equivalent to 0.05 as a base, and the height is 5. So we can actually see if we have 2 bases, 2 squares, a matter of fact, we can say 2 squares, okay, multiply by 0, which is a base, 0.005, multiply by 5, right? And that will be our area in that region that we have no definite shape. Okay, so I'm going to put an arrow right there. So all of this region below this graph is equal to 2 multiplied by 0.005 times 5. All right, so now let's put this together here in the question part or on the answer sheet itself and work it out to see exactly what we get as our answer. So here we're going to use the graph to determine that. Let's go back into a zoom. All right, so determine the work done. So we establish here our half base times height, which is this first part here. Let's put that piece in first. Half the base times the height. So what I'm going to say here, I'm going to say 0.029, okay, multiplied by 33, and let's say divide by 2, okay? So all of this now, all right, so very important, all of this will give us, as the work done on that part alone, it is 0.48, okay? The next part is the rectangular part, okay? And so the rectangular part here, let's go down to that part, which is base times height, and let's go back to the graph to see exactly what those numbers are. So it's going to be 0.016, all right, multiplied by 33, and that will give us, let's put that down first, 0.016. So it's going to be 0.016 multiplied by 33, okay, and that now will equal to, here it is 0.53. So it's going to be 0.053, okay. Actually, it is not 0.05 but 0.53. Okay, great. All right, and then now let's go to the top part that we have done up here, the estimated part, which was 2. Let me just quickly say, okay, so 2 multiplied by that. Okay, let's put it on the bottom here now. It's going to be 2. All right, I'll put the answer here as well. It's going to be 2 multiplied by 0.005 multiplied by 5. Okay. And let me quickly calculate that. And so here we're going to have 2 multiplied by 0.005 multiplied by 5. That will give us 0.05. So this will be 0.05. Okay. And so to add up all of this now as a total, and these are all in joules, I could put joules here. Okay, so all joules, because again, they're all their separate work done on each part. Okay, so this is also joule, this is also joule. All right, or you could put it at the end of it. So I'm going to add up all these numbers now to get my final answer, okay, as the work done. And so that added to 0.53, added that to 0.48, which will give us approximately 1.06. So this is equal to so the work done, I'm just say work done here. So work is equal to 1.06 joules, or it could be in Newton meters. Okay, so that's the work done right there. All right, so the next part of the question, The next part of the question now reads that beyond point A, the spring undergoes inelastic deformation. Explain the term inelastic deformation. And so this is when, so I'm going to explain that. So this is when a force causes the spring to stretch beyond its elastic limit. All right, so that's very important. So the force as applied to it will cause the spring to stretch beyond its elastic limit, and resulting in, I'm going to say resulting in a permanent damage to the spring. Okay, very important. So permanent damage is done to the spring. All right, and so just to make a point right there, okay, just to make a point real quick. So therefore, okay, I'm going to say therefore, all right, so therefore the spring will no longer obeys Hooke's law. All right. So in other words, there will be no more proportionality. Okay. All right. So this is where we end with this question. All right. I will try to see how much more question I could do. All right. So be safe and be good.